Hey guys, it's Chris Mattmann. How are you doing? Welcome to your lecture on intelligent information retrieval and web search. Today we're basically going to be talking about what information retrieval is. Information retrieval, or IR, has been around for a long time, in computer science, many decades. And basically what we're talking about there is, in terms of a library, in terms of the web, in terms of content that we're collecting, we're talking about a method of indexing content, in this case, a lot of times coming out of the library community, but even now into search engines, indexing documents or textual documents, and the method for by which we retrieve those documents and those documents that are relevant to a query that we have. A lot of people feel that IR has sort of become a killer app as it relates to the World Wide Web and search engines and so forth. And ultimately, it's one of the core kind of canonical subjects in this class. So there's been a lot of research to date. You can think about it in terms of web crawling and so forth, what we've talked so far, in terms of how to index a set of documents or a corpus, and then how to efficiently retrieve them. So if we talk about sort of a traditional information retrieval system, we're really talking about a set of documents or a corpus that are going to go into that IR system. And then we're talking about a user who's interested in finding those documents. The user is going to issue some sort of query string to the IR system, and we expect that the IR system is going to give us back a set of ranked documents, right? Probably a list sorted in some order, and so forth, and hopefully that order makes sense to the user. So a little bit about the history of information retrieval. You go back to the 60s and the 70s. Really what they were thinking about is information retrieval in terms of finding documents. And there were a lot of documents related to science back then, a lot of scientists and mathematicians that were trying to figure out sort of what was going on in information retrieval. And a lot of business and other sort of corporate and law documents that needed finding. It was a real big era because the two ultimate sort of query retrieval models were developed, the basic versions of them back then. The Boolean model, which we'll talk about later, if you're familiar with database systems, you should be familiar with that. And something that you might not be familiar with, but is really one of the kind of key subjects in this class, which is the vector space query model of retrieval. So Professor Salton at Cornell University were real big leading researchers kind of in this era. So by the time you get to the 80s, you've got IR has grown enough to a field where there's been, decades of sort of foundational research, and at that point you started to see companies that were simply devoted to information retrieval. So some real major ones are things like LexisNexis, which is a company that's devoted to basically document retrieval and storage and big data nowadays, and they deal with legal, corporate, government, academic, and regulatory markets. There's a company called Dialog in the 80s that sort of pops up. They have about 1.4 billion unique records of information, and they're able to manage it with an information retrieval system and product. And you started to see things like IR systems pop up within the context of the government, right? The National Library of Medicine puts out Medline, right? PubMed is becoming popular around the same time with the NIH for paper retrieval, for scientific paper retrieval. Okay. You get to the 90s, and with all the proliferation of content that starts to happen with the World Wide Web, ultimately, like we talked about, the initial things that started appearing and that really needed searching were file transfer protocol servers. So we needed ways of basically finding documents that scientists and other researchers would put on to FTP servers across the internet, right? So we talked about systems like Archie and Waze, right? So that was sort of the early, the kind of predecessor sort of to the web. Now web comes around and search engines start to appear, and ultimately search engines start to borrow a lot of ideas from information retrieval in general. In the 90s, you also saw sort of IR achieve a level of maturity that you started to see conferences that were entirely devoted to text retrieval and information retrieval. TREC was started by NIST, the text retrieval conferences. TREC has competitions in which researchers try and develop new and interesting and better methods to find and to index and retrieve documents. There are challenges that are issued, teams are formed, and TREC is still very popular today. We also started to see things like recommender systems come out of the AI community that tried to couple sort of information retrieval components, right? Basically finding content like movies, books, music, web pages that a user might be interested in, given some information that were collected about users in their profile and other sort of potential interesting characteristics. You started to see the development of what is immensely popular nowadays and what was made popular by Netflix and Amazon and other sort of product companies, which is started to see the development of recommendation systems and collaborative filtering style algorithms, right? So based on your preferences, what you've bought before, you might be interested in buying this, or you might be interested in this book or this music or this movie, right? So you start to see sort of the beginnings of what we call today collaborative filtering. Okay? Automated text categorization and clustering started to appear around the same time, because ultimately if we can find documents and we can rank them, or we can basically find documents that are similar or near similar, we can group related documents and started to group them sort of in the area of things like news and other kind of categories. In 2000, really talking about information retrieval as it's related to web search. One of the key elements there was link analysis, because we were dealing with things like ranking algorithms that weren't entirely based on text. All right. We started to think about how we could sort of extend IR systems beyond text as well into things like multimedia, so images, music, video. That's actually why I'm at DARPA. The past couple days, why I'm not there today is I'm actually part of a program to build a next generation sort of deep web or multimedia and other type of content, images, music, other type of content search. Right, this MEMX program is related to that. In addition, you started to see sort of IR systems as question answering systems, right? So they're returning an answer to a user's question rather than sort of a ranked list of documents. And TREC has an entire question and answer track related to this, and you can find it at the link provided here on the slides. If you break down information retrieval into a set of sort of CS areas, you're really talking about 5 basic areas. You're talking about database management, library and information science, artificial intelligence, NLP or natural language processing, and ML or machine learning. We'll talk about each of them in the next few slides. So if you really think about database management, it's different from than information retrieval. Database management is really talking about sort of structured data, right? It's talking about structured data that's stored in tables that we call entities, right? And the entities that are related together, right, through things like foreign key relationships. Those entities have structured data according to columns, right, that you define ahead of time, including their names and their types. And the rows within those entities or those tables are the actual instances of that structured data in the database, right? So a lot of times IR focuses on unstructured data, whereas database management systems focus on structured data. In addition, database management systems are focused on sort of retrieval of information in a well-defined sort of formal query language, this structured query language, which really came out of IBM sort of in the 70s and so forth, and was really based on mathematics and set retrieval and things like that. So SQL has very clear semantics in terms of things like projections, which are selections of particular attributes. It has semantics in terms of a particular way that they're going to retrieve and include elements in the query. It has a particular query model, which is a Boolean query model, and we'll talk about that. And what we found out is that, in general, although the early sort of feeling was that databases would be very useful in the context of web search, is that it was sort of difficult at some level in terms of taking web pages, which are mostly unstructured, and then trying to represent them sort of efficiently in a sort of relational model like in a database in terms of storage as well as retrieval. You can leverage things like the document object model in web pages to make some clues and to make the documents more structured, but ultimately what we found on the web is that Lots of web documents don't follow that nice model. In terms of library and information science, IR is really related to that domain. It's something that really kind of had a lot of influence and came out of that domain. Basically, as it relates to sort of library and information science, we're talking about IR systems as user interfaces, as finding documents, as humans interacting with them, as categorizing knowledge. Okay. Library and information science also really kind of came out with things like citations, right? The card catalog system, right? Organization, how do we organize documents, which documents cite other documents, which are related, and so on and so forth. And really what sprung out of this recently within the last 15 or 20 years is a real strong work that in the digital library community. So how do we take library and information science and bring them digital? Right? A lot of the big data things that are happening now have a lot of influence from digital libraries in that community, and they also have their own set of conferences. It's called the Joint Conference on Digital Libraries as well, just like TREC. AI is another field heavily related to information retrieval. In AI, we're talking about representation of knowledge, reasoning about it, and some type of intelligent action. There's lots of ways to represent knowledge in AI. There's first-order predicate logic, right, which is a query sort of mechanism and a system to sort of reason over a specific sort of domain of discourse. There are Bayesian networks for dealing with partial information, right, and decision choices, right, and the dependencies between the decisions that you're making. So AI, as it sort of relates to information retrieval, has really kind of come in the form of things like the semantic web, right? So how do we represent knowledge about documents on the web? How do we reason about that knowledge? How do we issue queries that can deal with partial information related to that knowledge? And how can we sort of glean previously sort of unknown knowledge from documents by doing things like reasoning? So the web ontology language is a way to represent information in web documents, and it's a way to perform things like inference over queries that are related to those documents. There's been a long history of the AI community in the both form of document and textual and metadata information, as well as in the form of things like ranking and partial information related to sifting between choices related to sort of retrieval of documents. Natural language processing, which focuses on sort of the syntactic, semantic, and pragmatic analysis of natural language text and its discourse. It has a real big relation in information retrieval, especially when we deal with things like queries and their structure, like phrase structure, right? And trying to understand the meaning of sort of a bag of keywords. NLP can really help us related to that. Arguably, things like a text retrieval model came out of the NLP community, models for queries, and so on and so forth. The feeling early on was that we could issue sort of NLP type of queries to search engines, and that ultimately they would respond back and give us the types of documents that we were interested in. Found out later that that wasn't exactly the case. A lot of search engines now discourage long natural language queries because there's a lot of information, and we'll find this out later when we talk about things like stop words or when we talk about things like stemming. There's a lot of extra information that we provide in terms of language that aren't necessarily relevant to types of things that we're looking for, right? That they add value when we're speaking things to people or conveying meaning, but they don't necessarily add a lot of value in terms of retrieval systems or information retrieval where we're trying to find documents and represent their information. There's a lot of room for ambiguity. Machine learning, as it relates sort of to information retrieval, machine learning in general is a branch of artificial intelligence, basically focused on development of sort of algorithms that allow computers to sort of change or evolve their behavior based on empirical data. So a lot of machine learning systems kind of break down into two subtypes. Supervised learning is focused on sort of users and classification of existing examples, and then learning what we call a classifier based on user-trained data sort of from that. Unsupervised learning focuses on methods of clustering examples that may or may not have attributes or labels or descriptions of them into meaningful groups, right? So allowing the computer to do some of its own learning, figuring out of what's in what group or what's related to what, okay? So machine learning is distinct from data mining. Data mining is sort of focused on the discovery of previously unknown properties for data. Typically, we bring in data mining when we deal with things like query analysis and ranking and so on and so forth. Whereas in machine learning, we're really talking about either sort of human-in-the-loop labeled training and then learning something like a classifier from that in the supervised case, and then in the unsupervised case, basically looking at automatically determining what relates documents in this case, or what relates information into things like meaningful groups. So in general, that's sort of some of the history and fields and related fields in information retrieval. You start to ask yourself in information retrieval systems, how do we know basically when there's a set of results that satisfy user query? Like, how can we deal with that? And there are several ways to deal with that. Okay. First off, relevance is subjective, right? So relevance might have to do with how quick sort of the documents come back from a query, how relevant they are in terms of what the user's intent was, which isn't exactly always easy to guess, how important or authoritative the documents that are coming back in the query are. You know, are they you know, the most highly cited documents ever? Are they from a trusted source? You know, are they from a very famous researcher or someone that we really respect, and so on and so forth. And then you know, how relevant are these returned documents to what the user's need was? Okay, so we can basically define two formal measures of the how successful we are in terms of returning documents in a query and information retrieval system. And we'll define recall and precision, and then I'll illustrate them in a very simple example. Basically, recall is the ratio of the number of relevant documents that we return, given the set of all relevant documents in the database or the information retrieval system. Precision is the ratio of relevant documents that we return combined with the amount of irrelevant documents that we bring back as well. All right. Both are usually expressed as percentages, and I'm going to illustrate both here in a real quick example that I've cooked up for you. Okay, so on the screen right now, you guys should see a very simple information retrieval system. This has 6 documents in it, okay, ranging from topics about dogs and cats, right, to German shepherds, puppies, chihuahuas, birds. These are various types of animals, okay. There are several relevant documents related to dogs, right? D1 is definitely about dogs. D3 is about dogs. D4 is about dogs. I think I've misspelled chihuahuas here in D5. That's about dogs, and then D6 is not about dogs. So, in terms of our entire document set, D2 and D6 are not about dogs, but all the rest of them are, D1, D3, D4, and D5. Okay, so say we do a query for dogs, and we get back documents 1, 6, and 4, right? So 1, 6, and 4 here, okay? So if we were to try and define recall, right, we would basically say that we got back 2, okay, of the relevant documents about dogs, and there's 4 actually of them, right? There's the 2 that we retrieved, and then there's the 2 that we didn't, right? D3 and D5 here. Okay, so we retrieved half. Our recall was half. It was 50% of the relevant documents about dogs. Okay, now let's define what the precision is, right? So the precision is the number of relevant documents retrieved divided by the number of relevant documents retrieved combined with the number of irrelevant documents retrieved. So in this case, document 6, it's about birds, right? So if that's what came back, it's definitely irrelevant. And so thus, we have two relevant documents back over the set of the 2 relevant documents plus the 1 irrelevant document. So the precision in this case would be 66%. Okay, so basically 2 out of the every sort of 2 out of 3 documents in terms of precision is basically what we're kind of returning back there. Okay, so we have 50% recall and 66% precision in this particular example. So if you think about these measurements and we start to think about the different types of search that's out there and available in an information retrieval system, the simplest notion of relevance is querying for content as it appears verbatim in a document. We call this keyword search, right? So you notice in that prior example about dogs, it's possible that if that text, that I had to kind of cover each document here, like let's say document 6 simply consisted of the string birds, right? 4 consisted of puppies, and so on and so forth. The simplest form of search, keyword search against this, if we were looking for dogs, the only document that would really come back in our example is D1. All right, if we were doing strict keyword search, we were strictly looking for dogs. Okay. So, slightly less strict notion for that is taking a look at the amount or the frequency or the amount of words and where they occur in the document for what you're searching for. So, if we're searching for dogs, and the document happens to have there are dogs here, as a sentence, or dogs live in a house, or these other types of things, might be taking into account where we first found the word dog in the sentences or the text or the paragraphs that make up the document, right? Where we found it, how many times it occurred, and these types of things, right? Or viewing the document itself as a bag of words, right? Which is a frequently used terminology to kind of refer to this. Of course, there's a lot of problems with dealing with this type of search. First, it's not very flexible, right? It's not very flexible. It doesn't handle things like synonymous terms. For example, it wouldn't have found things like puppies, right? It wouldn't have known German shepherds were also dogs, okay, and things like that. Restaurant versus cafe, right? People's Republic of China versus China, these types of things. The other thing is that it may return irrelevant documents that include sort of ambiguous terms, right? In our dog example, if we're searching for things like German Shepherd, we might retrieve back documents on Germans and maybe shepherds, people that actually shepherded animals and things like that, right? Or here, we're looking for bat. Are we talking about a baseball bat or the mammal bat? And various other examples here, like apple or bit and things like that. So going beyond sort of just keyword matching and just thinking about how we can become more intelligent in dealing with information retrieval, we want to build systems that take into account basically the meaning of the words, and we want to figure that out somehow, right? We want to derive a model for what the user is querying or what you mean. So we want to take into account potentially the order of the words in the query. We want to take into account potentially direct or indirect feedback from a user. Did you click on the result that we presented to you in position 1 or position 2? You didn't. Oh, why? And then how can we figure that out? We want to take into account things like the authority or basically the importance of the source that we're pointing you at. Okay. So all of these various things lead to particular areas of research and have led to particular areas of research in search engines and information retrieval, right? Authority is dealing with things like potentially link analysis algorithms and looking for things like citation, right? User direct or indirect feedback is like basically looking at things as to whether the user clicked on a link or click-throughs and things like that, all right? The order of the words in a query is looking at things like phrase search and particular query models for that. Meaning is trying to derive synonyms and so on and so forth. Right? So all of these things led to particular advancements in areas in information retrieval. So we think about the type of detailed architecture that we need to support an information retrieval system that takes all of these things into account. You see we have components and boxes for things like searching. We have things like ranking, like I said, maybe to take into account importance or link analysis or citation or text importance. We've got an indexer. Potentially we have a database manager, right? That's part of our search engine. We might have to deal with a way for users to provide us both queries but also feedback, right? And things like that. So these are all the detailed components that we need to support kind of more advanced information retrieval. And that's why you see these components cropping up in our search engine lectures on crawlers and things, because they kind of bleed into this. They collect documents. They help to provide us information to rank them. This is why you see query operations and query components and query models sort of bleeding into this and sort of dealing with this and so forth. So this helps to kind of suggest what type of architecture we need. So, you take this into account, right? You start to think about the system components, right? Well, of course we need a way for the documents that we retrieve to get information out of them, all right? And so we call this parsing, okay, typically. So parsing takes in a document or a piece of content, and it somehow forms or summarizes that document, typically in words, right, or what we call tokens. So a lot of times in doing this, we do things like pre-processing of those tokens. We may do things like stop word removal. We may remove common articles, a, the, and, it. Things that may not have particular meaning when users are querying, because we typically don't receive queries that look like natural language, like I am looking for this or whatever. People have learned to really summarize what they're interested in and provide these types of keywords and these types of models, and so a lot of time we've found in these types of systems, in IR systems, that we can remove out things like these stop words that don't really necessarily present meaning outside of sort of the spoken sentence or things like that. They don't have necessary relevance to the query. We might also do things like stemming. We might figure out the root of a word. Okay, we might take a look at words like removal, right, and realize that it might have a root word of remove. Okay, so if someone's searching for remove or stop word remove, they may be looking for stop word removal and vice versa. Okay, so we can take words and we can somehow stem them and find out its root word and come up with a set of synonyms and so forth that we can both use in terms of indexing as well as in query processing and so on and so forth. So the indexing process in an IR system constructs an inverted index of word to document pointer. So what it does is it takes these words that we parse out or we extract from our document, builds an inverted index that maps those words to documents in which they occur. Okay? And this is the type of index that we want because people are searching for words in these types of IR systems. They're typing words, and we need somehow to map documents back to those words that they're searching for. So searching, in the process of searching, ultimately retrieves documents that match a query in the form of words, right? In which those queries typically include tokens from that inverted index. And ultimately, ranking in an IR system takes the retrieved documents and then arranges them according to some order of precedence or relevance metric. All right? Okay, now we're going to talk about two query models, basically, that are going to implement sort of the retrieval models that we're talking about for an IR system. And it's going to implement and take into account these things that we care about, that we previously mentioned. It's going to take into account parsing and the tokens that we extract and our ability to sort of match those tokens to user queries. It's going to take into account a ranking model for basically ordering the results back, from those user queries. It's going to take into account pre-processing and other efforts that we need to do to sometimes match up the queries to what's going on in the documents or synonym detection and things like that. So we define these as query models, and we're going to talk about two particular query models here. Actually, we're going to talk about three. We're going to discuss sort of fuzzy as sort of the fuzzy query model as a specialization of the vector model, and we'll talk about that very briefly at the end of the lecture. So basically, a retrieval model specifies, number one, the representation of a document in our information retrieval system, be it a database, be it a text index, or whatever. It just specifies the details of the ways the documents are represented. It specifies a query model, a way that a user presents queries to the IR system and retrieves those documents back. And it also specifies a function by which we map the queries to the relevant set of documents that come back in the query. Relevance is subjective, but in these particular models, we'll define exactly how it's computed. All right, and note also that relevance can be binary or continuous, right? So binary means that everything is relevant that matches in the query, and we see this a lot in database type of models for that, or it's potentially continuous. Relevance simply ranks, or in the form of ranked retrieval, it ranks through some function or score what documents, sort of how important they are in the set of sort of result documents that come back. And it's possible that some may be less important than others, but it's not binary. It's not either important or not important. It's sort of on a gradient for that. So three major IR models that leverage A, fulfill these properties and define them are, and B, that sort of we're going to talk about here, Boolean models, which are set theoretic models. These are used in databases a lot. Vector space models, or statistical or algebraic, and then probabilistic models as a little bit of a specialization on some of the vector space models. All right, let's talk about some of the common preprocessing steps that happen in IR systems as related to search, especially as we deal with the web. And these are the types of preprocessing, like we talked about, like stop words. These are more kind of common preprocessing steps. So some of them, besides stop words, including stripping unwanted characters or markup from the text that's coming in. For example, this is what Tika does. This is one of the things that Tika does. For example, takes a document, be it PDF, HTML, an image, whatever, and it decimates it. It basically strips out any unwanted characters or markup, potentially, and strips it down to its text. Other preprocessing steps that we do a lot is tokenization, which is breaking down the text into keywords or tokens, and typically this is defined by some function. Sometimes it could be white space, it could be commas. You guys in your assignment 1 are going to be dealing with it for tabs, and so on and so forth. Stemming is another common preprocessing step. It takes tokens and tries to compute their root words. Computational, for example, its root word is compute. So if someone is looking for a computational documents that include those words should also match. Stop words, of course, which we have seen before. Detecting common phrases. So this is using like a thesaurus or looking at synonyms and things like that. And ultimately, these all lend themselves towards taking a document and indexing it somehow. Ultimately, building an inverted index in particular, which is a mapping of keywords that a user may issue as a query to a list of docs that contain, or documents that contain those keywords, or that particular keyword. So in the Boolean model, a document is represented as a set of keywords, right? Queries are Boolean expressions of those keywords. Basically, they're connected by Boolean expressions, which are operators like and, or, not. Some are unary, right? Some are binary. Here below in our example, we use brackets to indicate scope. It's a query for Rio and Brazil, or Hilo and Hawaii, and a hotel and not Hilton, right? So we're expecting this particular query to output documents that are in Rio and Brazil, or Hilo and Hawaii, and that contain information about hotels that aren't the Hilton hotels. Okay, and in the Boolean model, all of the documents that come back in response to that query should be relevant. Okay, we should retrieve no documents that are not relevant to this. There's no partial matches. Okay, so this is the type of thing you see in a database a lot. A database, the query result set, or the document result set, are all of the results that match basically your projection over the attributes that you're interested in. All right, so that's basically what's happening in the Boolean model. In terms of the Boolean retrieval model, basically what we're looking at there is not really much ranking, right? Ranking is really simplistic in the form of ordering, typically on one of the field properties of the document, ascending or descending, right? And there are simplistic ways to do that. You can extend Boolean models to include ranking. It's not typically done, but it exists sometimes. And what we see a lot is that Boolean models are very easy to understand for simple queries. It's a clean sort of representation, and you tend to find reasonably efficient sort of implementations for this. There are some problems, of course, in the Boolean model. It's very rigid, right? And means all, or means any. That's it, right? And means it has to satisfy all of those criteria. So if you put and into your query, you will not receive documents back that contain partial matches to basically the projections that you provided or the restrictions that you provided into your query. It's also very difficult to express complex user requests in this, so we have to provide sort of very intelligent interfaces to users, very complex interfaces to users to provide Boolean queries in the Boolean retrieval model. It's very difficult to control the number of documents retrieved in this model, right? All matched documents are returned. There's no sort of explicit notion, potentially, of pagination, right? Because there's no explicit ranking most of the time. So this is why database implement limit, some implement limit, but the SQL query language doesn't necessarily define it very well or in a standard fashion, right? Some databases implement limit, some don't, right? Some have different keywords for that. so on and so forth. It's difficult to rank the output, right? All matched documents technically, logically satisfy the query, right? So it's really hard to rank them. That's why you can order them by particular attributes in ascending or descending fashion, but ultimately it's really hard to kind of do that. It's also difficult to perform relevance feedback, right? So if the document's identified, by the user as relevant or it's irrelevant, how should we modify the query, right? Because all of these documents were supposed to satisfy the query, right? Because of its rigid sort of Boolean model for that. So it's not really exactly easy to figure out sort of where the user feedback comes in as well. So here's a sort of simple illustration of this, right? Take this simple query Lincoln, right? So if we just issue a query for Lincoln, our big problem is that it's going to match things like Lincoln Cars. It's a car manufacturer. It's going to match places like Lincoln, Nebraska. And it's going to match people, right, like Abraham Lincoln. So maybe we actually were intending it to match Abraham Lincoln, right? So we might add something to our query. We might say President and Lincoln, okay? Now what's going to happen here is we're going to get documents that both discuss the president of like the Ford Motor Company, because president will be present in those documents. And because those documents will likely include, because Ford makes the Lincoln car, information about Lincoln, we'll also get back irrelevant documents that have to do with the president of Ford Motor Cars dealing with one particular car model, Lincoln, right? So president and Lincoln isn't going to help us here. So we may say president and Lincoln and not automobile or car, scoping that. So this is a little better, but the problem is the not clause in this will basically remove a document that we may be interested in. For example, we may have a document that contains text like Lincoln's body departs Washington in a 9-car funeral train. All right, so here we're talking about the president, President Lincoln, and there's a document that's relevant to him. It's talking about, after his death, basically leaving Washington in a 9-car funeral train, and it's not going to come back in our query. So maybe we'd say President and Lincoln and biography and life and birthplace and Gettysburg and not automobile and car. But of course, too many restrictions can mean we're going to get nothing back. So we might say President and Lincoln and biography or life or birthplace or Gettysburg and not automobile. And it just becomes very difficult. So let's talk about some of the advantages of the vector space model, sort of in contrast to this. So the vector space model basically assumes that after all of those pre-processing steps that we do, that we discuss, the stripping, the stemming, and so on and so forth, we have T distinct terms that represent the document. So call these the index terms or the vocabulary for that, okay? And call the set of all documents sort of terms, T distinct terms after this, sort of the term, all of the terms in the index or the vocabulary for that. So basically these orthogonal terms form a vector space, right? The size of the vocabulary that we have, right, is the dimension that we have in terms of the number of terms. Now, take a document which is represented by a vector of these particular index terms, right? It contains these terms in them, these terms that are in our index, right? So document is DI1, DI2, or basically DIJ represents the jth term and the weight of the jth term in the document, all right? So the importance of that term in the document, right? And so we'll talk about how the weight's computed in that in a second. So what we can do is we can say, look, a document is described with terms, potentially having weights, for those terms. And the index itself, right, is a set of those terms. It's a set of those terms that map to the document, right? So this basically means that we can express documents and we can express queries against those documents as t-dimensional vectors or vectors that correspond to some selection or projection against those terms. So here's a little bit of a graphical representation. So let's take a vocabulary that has 3 terms, right, with the weights of the coefficients for that. And then let's say that there's 2 documents, D1 and D2, and there's a query queue. So here's a simple example. Right, so document 1 has 3 terms in it, T1, T2, and T3, right, with the associated weights, right, basically suggesting that the most important term is T3 because it has a value of 5 by it. Next most important is T2, and then, of course, the least important is T1. Okay, we've got another document D2. In this case, the second term in it is really important. It has a weight of 7. The next most important is T1, and the least important is T3. It's an implicit weight of 1. And so let's say we have a query, right, that's searching our information retrieval system and our index, and it presents to us a set of these terms that are also present in the document, right? It's a query against ultimately the third term, right? Because we're basically sort of zeroing out terms 1 and 2. It includes the third term, and it has sort of a relevant importance in terms of that query of 2, right? It's putting an emphasis of 2 on that. So we can graphically depict this, right? We can basically draw in a sort of vector space of the terms in terms of t dimensions. There's 3 total terms in our index, and we can basically say that the query is a query against the third term, right? And we can draw sort of the relevant weight of that in terms of its height on that particular axis for T3, right? And we can also draw basically where document 1 and document 2 lie on that space, right? We see that document 2 basically has an importance in terms of that T3 of 5, so we may draw a dotted line up here around the 5. And then in terms of the other dimensions, say for T2, it has a value of 3 on that, right? So basically, it's got a value down here of 3 for that. And then it has on the value of T1 a value of 2, right? So this is the document, right? This plane right here is ultimately document 1, right? We can see on the plane as well the importance of document 2. Related to that, right? And so on and so forth. So when we look visually at this, we can see ultimately where the sort of intersection of a query should sort of lie with respect to that. Okay, so this is just showing sort of graphically that model and how it represents it. So, you can look at this and say, look, is document 1 or document 2 more similar to the query? And how do we measure this, right? You can think about it in this sort of t-dimensional space. Well, there are various ways to measure similarity of documents in that space related to that. You could look at the distance of the documents away from the query. You could look at the angle or projection, and guess what? This turns out to be the way that we basically define these sort of similarity metrics with respect to that. So let's imagine that D1, D2, all the way up to Dn, right, is our document collection that we have here in the vector space model. And let's imagine that those documents contain a finite set of terms, right, that are effectively tags or words present after tokenization and the various pre-processing steps in those documents. The distinct set of terms present across all of them. We can draw those as columns in a matrix, and we can draw the documents themselves as the rows, right? And then we can define weights in terms of the relevant amount of importance it is if that term occurs in a particular document, right? And we can basically create a matrix like this. So an entry in the matrix corresponds to the weight of a term in the document. 0 means the term has no significance or it doesn't exist in the document, right? So we still need a way to compute the weight. So guess what? One of the ways we can compute the weight in there is to compute the term's frequency. And this was one of the early methods, the term frequency, to basically determine how important it is for if a term appears in a document, right? So in term frequency, basically the idea is the way to compute the weight is that more frequently occurring terms in a document are more important, right? Maybe they're more indicative of the topic, that particular term, right? Or that particular set of terms that the user is querying against, all right? So let's define f of I sub j as the frequency of term I in document j, right? How many times it occurs in document j. Sometimes you take term frequency and you might want to normalize it across the entire corpus. You might just want to take the frequency of, might want to take the frequency of term I in document j, and you might want to divide it by the maximum frequency, and that just simply normalizes it. Okay, you could do that or you cannot. Either way, term frequency is the frequency of term I in document j, and that's a valid way to compute the weight for our matrix. So terms that appear in many different documents, however, are less indicative of an overall topic, right? They're not unique to a particular document. They don't really distinguish the document if they appear in many different documents, right? So we might basically take into account something that we call inverse document frequency, right? So basically, we might take a look at the following measurements. We might look at df, which is df of I is the document frequency of term I, right? It's the number of documents containing term I in our entire index or our entire set of documents. We might look at something called IDF, which is inverse document frequency. It's the inverse document frequency of term I. Basically, it's an indication of, and the combination of these things, df or IDF, is an indication of the term's discrimination power in the document. All right? So n over df is the total number of documents, right, divided by the document frequency of term I, the number of documents that contain that term, right? So let's say 5 documents contain the term dog, right? And there's 10 total documents in our index, right? So if we don't take the log, we might take the log to dampen the effect related to term frequency. But let's say we don't take the log. Here we would have 10 over 5, or 2, right? So IDF of dog in an index in which dog appears 5 times in a total of 10 documents would be 2. Now we could take the log base 2 of that, which would simply be 1, right? That simply dampens its effect. Some people take the log base 2 here, some people just say n over df for that, for IDF, okay? So inverse document frequency just simply tells you how sort of discriminating the term is in your entire index. Basically helps you compute whether or not the term itself appears in many different documents, okay? So it gives you some sort of dampening effect. So if you think about term frequency and you think about inverse document frequency for that, a lot of times people combine it into term frequency IDF or term frequency inverse document frequency. They use this to compute the weights, right? They might say the weights in our column matrix, right? And recall again that our rows are documents and our columns are terms. We might say that the weights, which go in the IJ slot, right, or the document I term J, is the term frequency in terms of document I in term J, times by the inverse document frequency. In other words, how many times does that term appear in a particular document times by how many times overall that term appears in the index, right? And so this could be term frequency times by, and if we dampen it with the log base 2 of n over df for that. So basically what this particular computation will do is it will take a term that occurs frequently in a document, but not very much in the rest of our document collection, and you'll give it high weight, right? So this is clearly a term that's highly indicative of this particular document. So when a user queries against it, this is the document we want to return because it's not appearing lots in other documents, it's only appearing in this document and it's appearing a lot of times, right? So that gives us basically a measurement in that sort of vein. So lots of other ways of determining the term weights have been proposed, but TF-IDF has been found to work very well and is still used today in things like Lucene and Solar and so on and so forth as a basic, very good overall metric to determine the relative mapping of a user query to that sort of vector space model and to figure out the weights. So here's a very simple example. If we have a document that has 3 terms, A, B, and C, with the given frequencies, A occurs 3 times, B occurs 2 times, and C occurs 1 time. Assume that a collection has 10,000 documents, and overall the document frequencies of the 3 terms A, B, and C are A appears overall in 50 documents, B appears in 1,300 documents, and C appears overall in 250 documents. Okay, but if we're basically trying to figure out the TF-IDF for that first document that has all 3 terms, A, B, and C, well, we would first compute the term frequency in that document of A, right, which is it appears 3 times, and the maximum number of times, you'll recall, that it appears across any document is 3 times. for that. So the TF, or the term frequency there, is 1. The inverse document frequency, again, is the total number of documents in our index, so 10,000, divided by the total number of times that this particular term appears, so that's 10,000 divided by 50, and then take the log base 2 of that, okay, which amounts to 5.3. Right, so the TF IDF here is 5.3. So for term B, basically B occurs twice in this document. Maximum across all the documents that a term appears is A, which appears 3 times, okay? And so we have term frequency is 2. 2 out of the maximum times that a term occurs, so it's 2 out of 3, all right? And again, to compute the inverse document frequency, we take 10,000 and say, look, B occurs in 1,300 of them. And we take the log base 2 of that, and that's 2.0. And so here we take 2/3 and we multiply it by 2.0, right, which is ultimately 4/3, right, or 1.3. C follows suit. C appears 1 time out of maximum times of 3, so we have 1/3. The IDF is log base 2 of 10,000 divided by 250, which is 3.7, and we have 3.7 times by 1/3, or 1.2, right? So these are relevant measurements. So this is basically saying, look, if the term A occurs in your document, basically, overall, it's only appearing in 50 out of 10,000 documents, and it appears 3 times, it's a really good indicator that A, if a user is searching for the term A, they want this document to come back for it, okay? Whereas B or C, B and C occur quite a number of times in other documents. They don't occur tons of times in this document, 2 times or 1 time. They're not real good discriminators for that. So now let's discuss some issues with the vector space model, right? So one of the issues now, I mean, we have a fairly good way to compute the weights, to compute the relative importance of a user query, and map that query to what document should come back with something like term frequency over inverse document frequency. Now, how do we determine what are the important words in a document? What are other ways? So one common way is for people to compute n-grams. Basically what these are phrases or idioms, and to map those to the terms as well. What these are contiguous sequences of n items in a given sequence of text or speech. Usually an n-gram is any combination of letters, but it could also be syllables, words, base pairs. So an n-gram of size 1 is usually a unigram, size 2 is a bigram, size 3 is a trigram, and so on and so forth. So some of the questions you might ask yourself is, how do we determine the degree of importance of a term within a document and within the entire collection? How can we figure out the similarity between a document and the query, right? What are the effects if this is a web information retrieval system? What are the effects of links and formatting information for that? And how do we sort of deal with this? Well, we need some similarity measure, which is a function that computes the degree of similarity between two vectors. In this case, our vector for our query terms and our vector of terms and potentially weights that represent our document, right? So using a similarity measure between the query and the document, we can basically rank the retrieved documents in the order of relevance, basically, that we presume for that. And it's possible to have a threshold so that we may only return some of the results and then allow people, for example, to page through them in various ways. So one similarity measurement that can be done is sort of the inner product. Basically, it takes sort of 2 vectors, takes the one for document D and the one for the query Q, and we compute an inner product in the form of we take their weights. We take the relevant weights of our query, we take the relevant weights of our document, and so forth, and we multiply them over all of the terms in both of our query and all of the terms in our document, right? And then we sum basically the results of that multiplication. Right here, where Wij is the weight of term I in document J, and Wiq is the weight of term I in the query. Okay. So for binary vectors, the inner product is basically the number of matched query terms in the document. Right. So if the weights in terms of something like the query are binary, in other words, if they include the term or they don't, then it's very easy to use the inner product to basically see which terms from the query match in the document, right? Because it's the size overall of the intersection of that inner product. For weighted term vectors, basically it's the sum of the products of the weights of the matched terms, okay? So, some of the limitations of using inner product for this: the inner product is unbounded, can get very large potentially. It also favors long documents with large amounts of unique terms for that. It can measure how many terms are matched, but not necessarily how many terms are not matched, right? So it does have some limitations. Here are some examples. We have a query here, basically for retrieval, for architecture, and for management, and for information. And that's our query, and it's denoted by a binary vector of 1 on the term retrieval, 0 on the term database, 1 on the term architecture, 0 on the term computer, 0 on the term text, 1 on the term management, and 1 on the term information. We have a document that has the following tokens denoted by the binary vector: retrieval, database, architecture, text, management, and information in that, right? Again, the size of the vector is the size of the vocabulary we're dealing with, so it's 7. 0 here means that the corresponding term is not found in the document or the query. So the similarity of the document, D to Q here, the inner product, right, again, is the sum of the multiplication of the weights, in this sense, here, the vectors, for the document and the query, which, if you multiply them out, it's 1 times 1 for retrieval, 1 times 0 for database, 1 times 1 for architecture, 0 times 0 for computer, 1 times 0 for text, 1 times 1 for management, and 1 times 0 for information. Ultimately, there are 3 matches, and we sum them together, and it's 3. So that's the similarity of the document to the query. We can take a weight. We can take a weighted version of this, right? If we pull in here a document, it has 3 terms. We pull our weights back, 2, 3, and 5. We pull in another document. It has weights of 3, 7, and 1 on terms of terms 1 through 3. We have a query against terms 1 through 3 that only includes term 3. We can basically compute the similarity of document D1 to that query and the similarity of document D2 to that query by computing that product. We basically find that document D1 has a higher value in terms of its match to the query than D2 does, right? And if you look at it, this is probably true, right? Because the query is looking for term 3. It's saying that it has a weighted importance of 2. We note that document 1, in this case, has actually does have, when matching term 3, a weighted value of 5 on it, as opposed to document 2, which only has a weighted value of 1, right, for that. So 5 times 2 is 10, 5 times 1 is, or 2 times 1 is 2, and ultimately, if we match here, document 1 will be much more relevant to query Q than the other document. Other similarity measurements are cosine similarity. I'm not going to go into a ton of detail here, but it basically exploits the feature space, like we discussed. If we mapped a t-dimensional term vector onto planar space, basically trying to find out the similarity between vectors, and we can use cosine similarity for that. Okay. Basically, it's the inner product. It measures the cosine of the angle between 2 vectors, and it's basically the inner product normalized by the vector lengths. Not going to go into a ton of detail on it. It performs okay, probably no better simply than taking sort of the multiplication of the inner product in the previous sort of measurement. Okay. I'm not going to go into detail here on the cosine similarity test. I leave this sort of for you guys to review. Here again, this is just more detail on the cosine similarity. Some general comments on the vector space model. It's very simple. It's a mathematically sort of elegant approach. It considers both local term frequency and global inverse document frequency, the relative importance of the document across the entire corpus. It provides partial ranking and ranked results, or partial matching, that is, in ranked results. Works very well in practice, and it's very computationally efficient. Has some obvious weaknesses, but we tend to get around that. Very intelligent ranking models. And it's very efficient to implement for large document collections. There's some problems with it. right? There's no semantic information implicitly. It doesn't talk about synonyms per se unless you do some of that in the pre-processing step. It's missing syntactic information. It doesn't take into account phrase structure, word order, or proximity information. It assumes that all terms are independent in the document, and that's not necessarily true. That typically there's a relationship between those terms. It also doesn't provide necessarily a way to require that a term appears in a document, as you can in the Boolean model. Okay. I'm not going to go into a ton of detail, but there's also a probabilistic model, which allows us to basically compute the similarities between documents and queries as a probability that a document is relevant for a given query. So probabilistic theorems like Bayes' theorem are traditionally used in these models. This gives us one method of dealing with sort of term independence, because this allows us to define the relevance of a query to a particular document in its terms as a probability, which allows us to express some more fine-grained control of that term independence. I'm not going to go into a ton of detail on this here, but this is Bayes' theorem. Basically tells us and treats documents and terms appearing in documents as evidence that the document is relevant for a particular query. Okay, I'm not going to go into detail here on Bayes' theorem. And that's the end of your lecture. So I think one of the real key things to review is we really discuss kind of the history of information retrieval, its relationship to other computer science fields. We introduced, very importantly, I think, what we need to do to build an information retrieval system, a system for parsing, for indexing, discussing sort of the framework for things like inverted indexes, discussing query models, in particular the Boolean query model and the vector query model. And thank you for staying with me during this lecture. And we'll continue our discussion this week of discussing things like inverted indexing, and we're going to go over your homework on Thursday, your homework one that we've posted. So thank you very much, and I look forward to talking to you guys then.